Uh, so welcome everyone. This is the first session, live session um, for. Let me just share my screen. 1 second. All right. Just can someone please confirm whether my screen is visible? The slides, that is. We'll wait for a couple more minutes. People are still joining. We'll start in a couple of minutes. In the meantime, just let me know whether my screen is visible or not. Okay, fine, good. Um, so in the meantime, while the people are joining, so as you know, these are the live sessions. There'll be 12 live sessions, each 2 hour long, and then finally one final session for 1 hour. I'll be summarizing, or based on your request, if you have some specific requirements, in 1 hour we'll discuss that. Otherwise, I'll summarize or I'll talk about the what I feel is the most important topic for this course. So, as you know, this course is Fundamentals of Semiconductor Devices, run by NPTEL. NOC24E02 is the code. This is week 1, and my name is Amit. I'm a PhD scholar at ISC Bangalore, and I have a YouTube channel where I'll be uploading these videos. I'm recording these sessions, so each session I'll record. For some reason you're not able to join live, or let's say you want to watch the video or some part of it again, you can go to the YouTube channel. I'll share the link, just a minute. So this is the link, and and I'll also share the email ID. In case you already have you must be aware that this course has a discussion forum, right? So you are encouraged to use the discussion forum for solving your doubts, asking queries and so on, or let's say regarding some assignments or some content. This is my personal email ID. If you want some specific thing to be addressed, feel free to email me. I'll try to respond in a couple days time at max. So that is that. Now, before we start, I want to tell a bit something about myself. So here it is. As I told, I'm a PhD scholar. Oh, yeah, I'm actually, now it's 5th year. I have to update it at Center for Nanoscience and Engineering at ISC Bangalore. I work on a semiconductor called gallium nitride. This course in semiconductors. So I'll be taking a lot of examples and whenever possible from this semiconductor named gallium nitride. So just a brief outline. This is my research work. So the devices that you see on the top right is one which we fabricated in what we call a clean room. So this dimension, as you can see, is only a few hundred microns, and you see this feature, this is only a few hundreds of nanometers. So that's about that. My academic background, I have a BTech in electrical engineering some 10 years ago, and for the past 5 years I am a PhD scholar at ISC. I have taken a few courses on NPTEL and otherwise before, so this is some of the things. In fact, I was TA for this course twice, in 2021 and 2022. Um, I have a some industry experience also. And finally, I think, which is the most important thing, so these are the two email IDs. If you have any doubts or comments, please feel free to email me. I'll prefer you email me on the bottom email ID, that's learnwithamitbansal@gmail.com. So that's enough about myself. So what I'm going to do now, I first need to get an idea about the audience here. So for instance, so I have a few questions. I'll request you to just raise your hand in response that I'm asking. So as of now, there are around 18 to 20 people in this session right now. So can you just let me know how many are you from masters or PhD or higher? So two people. Okay, three. Okay, so this means you have completed. You are currently Sneha, Asmita, and Metallurgy online. Are you currently in PhD or in masters? Okay, the people who are in PhD, please raise their hands. Okay, two people, fine. And in masters, people who are currently doing their masters or have completed their masters. Okay, so I'll assume then the rest of the people around 17 which remain uh, are from bachelor's background. All right. So one more question regarding this. So among the bachelors, how many are you of from third or fourth year? I'll repeat. How many of you are from third or fourth year? Please raise your hands. Okay, three people. Fine. Um, how many are you from the first or second year of your bachelor's? First or second year. All right. So looks like 14. All right, 13 or 14. Fine. Because I have to now. While I'm preparing, you can lower your hands now. Thank you all. So okay, so this gives me an idea because why I ask these questions, because then I'll have to prepare my slides accordingly. So since the majority of the people who are here are from the first or second year of bachelor's, so I'll make sure that I start from the basics of stuff and then gradually build on. So for instance, I'll not straight away start from very those concepts which you may not have heard. I request the masters and the people who are higher, who have some experience, a background in semiconductor physics, to be more precise. Just require a bit of patience. Just don't worry. I'll gradually increase the level so that each of you, I hope to keep you engaged. All right. So that is all I think that I wanted to ask. Yeah. So final question from you is. What are your expectations from these sessions? This is important again because I know your background, so that will give me an idea about what the level, the content, how I should make. Now, how to present the content that I have made, I need to know that what are your expectations from these sessions. I have a few options. I'll just iterate them. Yeah, Shreya, go ahead.
No, sir, I raised by mistake, sorry.
Okay, fine. So I'll just put out a few options that I mean this is based on my experience and based on what NPTEL has during our training. NPTEL has asked us to do this. So that's why I'll put out some of the basic options. So first is that you will be attending these sessions primarily to solve how to solve the problems. I know that is the mandate, but you'll be primarily focused. How many people here will be interested only in solving problems, only in solving problems? Please raise your hands. Okay, fine, two people. Okay, how many people here would be interested in problem solving as well as some background on problem solving, as well as a brief background on that particular question? So for instance, let's say the question asks about what is the difference between direct and indirect band gap, or identify the indirect band gap semiconductors. So before solving the question, I'll also talk a bit about what is a direct band gap semiconductor versus indirect band gap semiconductor. So some concept, and then we go ahead to the problem. Okay, I see 8 concept plus problems. Okay, fine. Thank you. Um, yeah. So finally, third thing that is one of the common ones is how many people here would like me to go into concepts in detail. That means you have every week lectures are released, videos are released, 6 to 7 videos. So the Professor Digvijay Nath, who is the instructor for this course, talks about many concepts, for instance, right? So you want me to take one concept and go in detail for, let's say, 20 minutes or 25 minutes on one concept. No problems, just concept. How many people would be interested in that? All right, none. Fine. Fourth and the final thing is that the people are here just for a one-to-one guidance, not just for this specific course, but for some options in general. So, for instance, after bachelor's, you might want to do a master's and so on, or you want to write some exams like GATE and NET and so on. So how many people are interested in that part of the picture, that okay, we want some idea on how to proceed with our career? All right. So almost I'm seeing currently 12, 13. Okay, fine. Fine, I understood. Thank you. Right. So I have I hope I think I have a fairly good idea about what my audience is, and how should I make the content and how I should present it. Fine. I'll make sure that that when I'm solving the problems, I'll keep in mind the points that you have raised. Fine. Finally, I'll just before starting, we have 2 hour session. I have the slides ready. I mean, the content for week 1 is not that much. So if you want to say something that I might have missed, or you want to add something, please go ahead. We have time. You have some specific request, that is, I mean to say, or specific concern, feel free to ask. Just for the people who have joined a bit later, um, so in the chat box you can see my YouTube channel and my email ID. So as I've told other people before, each session of 2 hours that is conducted here online, I'm recording that as I speak, and I'll upload this recording in a few days time on the YouTube channel that I have mentioned in the chat box. So in case you want to revisit some particular part of this session, some particular problem, or in case you cannot attend any future sessions, this is for reference that you can go to the YouTube channel and watch. Secondly, I'll be uploading these slides that I am sharing. Let me share these slides right now. So every week I'll be preparing some slides. So these like for instance, you can see the first slide on your screen. So every week I'll be preparing some slides through which I'll be conducting this session, primarily through these slides. I'll also be uploading a PDF document of these slides on the Google Drive, and which you have access to. I mean, you can request the access. So yeah, I'll upload the video, and I'll also upload the PDF, and which you can see, for instance, you're solving your problems, or maybe when you're solving your assignments, and maybe when you want to write your final exam 4 months down the line. So yeah, any comments or questions for now? Otherwise, I'll start with the session for this week. All right. So let's go ahead. So as I mentioned, we'll be meeting for 13 sessions. First 12 sessions will be 2 hour long, and the final session will be 1 hour long. In the final session, I'll be summarizing some of the key points, or I'll be taking one specific topic if you have any such requests. Okay, just a second. All right. So I've spoken enough now, and now it's your turn to speak. So my first question to you is that it's a very fundamental question. In fact, the course itself says uh, fundamentals of semiconductor devices, right? So there are three words in that: fundamentals, semiconductor, and devices. So I'm more focused on the word semiconductor. To understand the word semiconductor, this is my question to you: what makes a material metal or insulator? Please raise your hand and or just speak. I'm not going to answer this question. We'll remain stuck on this slide until you guys speak up or write for that matter. Yes, Arvinda. Yes, please go ahead.
Sir, conductivity.
Conductivity. Which kind of conductivity? How many types of conductivities do you know? Are you aware of? How many?
Bandwidth,
Conductivity. Second, what was that?
the band gap,
Band gap.
Thermal conductivity.
Thermal conductivity. Okay. Thermal conductivity. Band gap. So okay. So my hint to you is that think of school level chemistry, 10th or 12th level, because the keys that I want to build up from that. So fine, conductivity is a concept which I believe is introduced in 8th or 10th standard. So thermal conductivity is also introduced, so that's fine. Band gap, yes, whoever said that, that is correct, but we'll build up to this band gap. I'm writing it, but we'll see how the band gap comes about. Okay, so yeah, any other guesses? Conductive, thermal conductivity, band gap, what else?
Electric conductivity.
Okay, electrical conductivity, very good. Anything else?
Doping.
Sorry?
Doping level.
Doping. Okay. Okay, so since someone has mentioned doping, I'll just take this question. What is doping? I mean, again, you have to explain it to me as you are explaining to a 16 or 17-year-old kid. So you have to explain doping to me in that sense. What is doping? It's fine. Take a guess. We'll reach there. Sorry?
Adding impurities.
Yes, very good. Adding impurities at the most simplest level. This is what it is. Adding impurities. And we'll see. In fact, in the coming, I think in the second or third week, we'll be talking about this doping in depth. Okay. Yes, very good. What else?
free
Anything?
electron,
Sorry?
free electrons.
Free electrons. Very good. Free electrons. Now, this is a term that I understand. For instance, electrons, high school, we are familiar with this concept. And free electrons means free. I'll just, to be more clear, I'll write here free electrons, not under influence of any electric field. I'm being very liberal here by writing this definition, but we'll see that how it shifts a bit from this. But yes, for starting point, this is a very good, in fact, this is very good understanding of between the difference between metal or insulator. Anything else that you want to add? All right, I'll write one from my side. I recall from I think that's 8th standard chemistry. When I was in that, I was told that metals shine. They are malleable. They are ductile. So I believe malleable is something that can be beaten into sheets. Ductile, you can make wires out of them. So these are some of the other properties of metallic materials: they shine, malleable, and ductile. Right? Fine. So I'll build up with this. I believe I have. Yes, Fatima.
Is doping done in metals also?
We'll come to that. The points that you people have listed, I'll go through them one by one, and we'll discuss them. Okay, so then nothing. I believe there's nothing more to add. So let's just talk about them one by one. So I'll leave the topic of band gap for a bit later, because I'll be coming to this in today's session itself. So let's leave this for now, band gap. Okay. Let's first talk about the points that I have added. Metals shine. Shine means they have a luster. For instance, gold, the jewelry that you see, gold, right? Gold is a metal. But all metals shine. That's not necessarily true. Some non-metals also shine. For instance, diamond. Diamond is a non-metal or insulator, so to speak. It shines beautifully. So this thing that all metals shine is not a sure shot method of saying that something is a metal or non-metal. Malleable means something which can be beaten into sheets, right? So for instance, you see aluminum foil, which is used to wrap food, for instance, right? But there is another material called graphite, which is made out of carbon. Carbon is a non-metal. This is an allotrope of carbon, and graphite sheets are in fact what is known, these single sheets are known as graphene. These are in fact one of the first of all, they exhibit semiconductor behavior, right? First of all. Second, the sheets, they can be we can grow sheets of them. So again, this property is not necessarily related to metals. Again, ductility is something, the wires that we talk about here are a few centimeter or a few meters in diameter. When you go to lower lengths, right, micrometer, nanometer, there are some other materials which are non-metallic, and we are still able to make wires of them, nanowires or nanotubes. So just to formally define, anything is any entity, physical entity, we say it nanowires or nanotubes, if one of its dimension, that is x, y or z, is less than equal to 1 nanometer, either one of them, either it's x dimension, y dimension or z dimension less than 1 nanometer, then we say it's a nanowire, or it's a nanomaterial rather. So for instance, it can have, as I told about graphene, so this thickness is, let's say, less than 1 nanometer, and this is not and these are, let's say, 50 micron and 20 micron. But since one dimension is in less than 1 nanometer, we call it a nanomaterial. So this property of distinguishing, which we had learnt in high school chemistry, does not stand free anymore. Free electrons is in fact rather one of the key ways of identifying a metallic material. So this in fact is true. They have free electrons. Doping, someone told at the basic level it's adding impurities, but I'll add to that, adding impurities at a very low level. What do I mean? How do I define very low? I mean, let's say parts per million. I'll compare this with an alloy. So for instance, stainless steel is an alloy. Stop a second. Wait a second. Someone's asking me whether nanomaterial is from 1 nanometer to 100 nanometers. Oh yes, actually you're correct. So it's not, I think it's not 1 nanometers, less than 1 micrometers. Sorry, you're correct. If its dimension is in 1 to 100 nanometers, or even a few hundred nanometers, we classify it as nanometer. The thing is that it's a matter of subjectivity. There's a bit of people based on their convenience call it, but yes, you're correct. This I had written it wrong. Not less than 1 nanometer, less than 1 micron. More or less, if it's less than 1 microns, you say it to be a nanomaterial. Okay. Alright, so I was talking about alloy. So for instance, stainless steel is an alloy. Stainless steel is an alloy of iron, carbon, and some nickel and cobalt. So it's I think more than 90-95% iron, and there's some trace impurities. how much, around, let's say, I'm forgetting, maybe carbon is 3% and so on. Here I'm talking about 1 parts in a million. So here if I like in terms of percentage, it will be 0.00001%, this much. So when we add impurities at such small levels, then we call it doping. So it's different from alloy. Alloy is usually higher percentage. Okay, dopings are very, very small, and a lot of efforts goes into controlling this amount, because this directly dictates the properties of any material. We'll come to the doping in, I think, second or third sessions, where we'll talk about these levels, that parts per million or parts per billion. How much are they? How do we quantify them? And what is their effect on the properties, particular electrical properties of semiconductors? Bandgap, I told, will come later in today's class. And conductivity, yes, electrical conductivity is one of the key ways of classifying rather materials between, just a second, of classifying materials, metallic or non-metallic, for that matter, or semiconductor. Thermal conductivity is also sometimes used to define, but then again we are talking, when we don't talk about solids or in powder form. So this definition, this thermal conductivity definition, sometimes breaks down, because diamond is a very good conductor of heat. For instance, silicon carbide is a semiconductor, is also a good conductor of heat. So there are things, I mean, not some metals definitely, for instance, copper, gold, silver, they are good conductors of heat. But again, as I was telling you, its definition is, I will say, free electrons, and we'll also relate these free electrons with band gap and electrical conductivity in the following sessions. So then next question arises is that, okay, fine, metal has free electrons and so on, non-metal does not have. What do we mean by semiconductor? Okay, just one thing, metal I'll use analogous with conductor. Okay, so I may use these words interchangeably. So now second question for you is, what is a semiconductor? You guys have told me what is a metal and what is an insulator. Now second question is, what is a semiconductor? Go ahead, speak up.
Whose band gap is less than 3 electron volt.
Okay, so band gap less than 3 electron volts. Fine. What else? Yeah, Arvind?
Sir, tuned conductivity.
Tuned conductivity. Very good. Anybody else? Some properties which if a material exhibits them, we'll say that that material is a semiconductor. Okay, I'll add one more point. You see the word semi usually means half. For instance, semicircle, and this is a full circle, and this is a semicircle. Semiconductor is something which is, as the word literally suggests, it's half conductor. So what does it mean? It means that the conductivity of semiconductor is more than of insulator, but less than conductivity of metals or conductivity of conductors. So that's what the word semi, the role of semi is explained by this. Okay, fine. Just to illustrate the previous point even further, so okay, so band gap of less than 3 eV, yes, they are semiconductors, but there are some semiconductors, for instance, as I told, gallium nitride, on which I work on, has band gap of 3.4 eV. We call this as wide bandgap semiconductor. Again, as I told you, we'll visit the concept of bandgap again. Where will these things will become more clear, and as we go ahead in this course, this bandgap will term will keep on appearing again and again, and you will get more clarity. And at any point of time, if you feel any doubt, just please speak up or raise your hand or write in chat box. I'll be more than happy to stop and explain. Right. So let me, so first point we'll discuss later. Third point, I want to emphasize it over here. So as I told you, this is the conductivity. On x-axis is the conductivity, bottom x-axis. Top right is the resistivity. So conductivity is so resistivity is nothing but 1 over conductivity. Simple as that. Right. So you can see that in the green we have semiconductors. They lie somewhere between insulators and metals. That's fine. We can have a material, let's say gallium arsenide. The key point, as someone pointed out, is tuned, or I'll rather say another word, tunable. This means, for instance, if you take silicon in this as an example, silicon can have the conductivity from 10 to the power minus 5 to 10 to the power 3 Siemens. S stands for Siemens per centimeter. Let's take the case of copper. So copper will have somewhere around 10 to the power 7. It's fixed. You cannot change that. Slightly, but not much. Not in the orders of magnitude which silicon can exhibit, from 10 to the power minus 4 to 10 to the power 3 Siemens per centimeter. Or gallium arsenide, it changes from 10 to the power minus 8 to 10 to the power 4. That's 12 orders. And how do I change that? As someone mentioned, doping. Just by adding impurities in the precise amount, or in a, not precise, in a controlled amount, you can control the conductivity of this material. And this is the beauty of semiconductors. Not that their conductivity lies in between insulators and metals, is that they can have any conductivity. So for instance, you have this material 1 based on gallium arsenide. I'll write the gallium arsenide 1, and this is gallium arsenide 2, and I'd add some impurities, I1 to this, I2 to this, or doping, right? Based on what I am doping, I1 and I2, what this material is, what is their concentration, I can have the conductivity of this material and this material drastically different from each other, which is not so common in metals or in insulators. Their conductivity is more or less fixed by nature. We cannot change them artificially. In semiconductors, we can do that. So that's the best identification of classic characteristic of a semiconductor is that tunable electrical conductivity. Okay, right. So that's enough about it. Now I'll come to the topic. I'll pause here. So if you have any comments or questions or doubts, feel free to ask. Okay, let's go ahead. So now I have given a very brief introduction about metal, insulator and semiconductor. Now from this point onwards, we'll be mainly focusing only on the semiconductors, as a course also is semiconductor devices. So we'll cater to that somewhere, I think in 1 or 2 sessions, I think especially on Schottky contacts, some metals will again come into the picture, but otherwise throughout we'll be talking about semiconductors 90% of the time. Okay, as someone told, it's a band gap. So let's understand that term. Band gap literally means there is something called a band, and there is a gap in the band. So on the right you can see that. So let's forget about why this name is called conduction band, why this valence. Let's see, there is a band. This means electrons can live here. So this is energy. On y-axis is your energy. This means, right, again, energy. This means electron can have this much energy, whatever this unit is. This energy, this energy, this energy, this energy, this energy, this energy, this energy. Anything it can have. It cannot have this energy. There is a gap. This is continuous. That's why it's called a band. This is another band, band 1, top band or bottom band. But in between, electrons cannot have this much energy. Why? We'll see in a minute. That's why it's called a band gap. So semiconductors exhibit a band gap. Insulators also exhibit a band gap. What's the difference? The band gap of insulators is very large, 9 eV, 10 eV, and so on. Okay, usually we express in terms of electron volts. It's a unit of energy. E is the electronic charge and V is the potential. So if you recall the energy, U equal to Q times V. U is the potential energy, Q is your charge, and V is your electric potential. So same units. You replace Q by E and you get the energy of, you get the joules. So that's why EV has the same dimensions as joules, right? So how does this come about? This is Professor Digvijay explains this in lecture slides in great detail. Essentially what's happening is, this is an example of silicon. So if I recall, silicon is 1s2, 2s2, 2p6, 3s2, and then I believe it's 3p2, 14 is the number. So yeah, 10, 14, yeah. So this is this is your silicon, an atom electronic configuration. So what happens is, when you bring a lot of, for instance, when you bring n such atoms of silicon close together, they tend to talk to each other. So here, for instance, when they are far apart, so y-axis is your energy, x-axis is your distance. When they are far apart, there are, so you can see 3p and 3s orbitals. So 3s are filled. There are n number of total atoms, so 2n states. They are filled with 2n electrons. p6, so p orbital can have maximum 6 states. So total n is the total number of atoms, 6n states, but there are only 2 atoms, 2n electrons. However, when you bring them close together, the orbitals tend to overlap, and ultimately such kind of thing happens, that you see, rather than, so here in this region you can see there is a continuum. There is no band gap over here at this distance. At distance a1 there is a continuum, there is no band gap. However, as you keep on bringing them close together, you can see a band being created. A0 is what is called a lattice constant. This is the equilibrium position. For any given temperature, any system crystal will have the lattice constant. This is the band gap that you are seeing. So you see, this is the top band that I was saying, top band and bottom band. Electrons, naturally every system will tend to have in its lowermost energy states. So total, how many electrons were there? 2n electrons plus 2n electrons, 4n electrons. And below there are 4n states. So all these 4n states will be filled with 4n electrons. The top 4n states will have 0 electrons at 0 Kelvin. When you increase the temperature, some of them will go there. We'll come to that again today. But for now, it's a very simplistic picture. There are atoms, n atoms. When you bring them close together, they tend to split in bands. Okay, very simple picture. What we can do, in fact, now we have established that there is a band. This means electrons can live here as well as electrons can live here. So I want to do something. I want to transfer electrons from the valence band. The bottom band is known as valence band. The top band is known as conduction band. Valence band, because the electrons are bound here. They are not free to move. The electrons here are free electrons. So semiconductors also have free electrons. It's not that only metals have. So in the first slide, when someone pointed out what is a metal, presence of free electrons, yes, semiconductors also can have free electrons. Okay, fine. So now what I want to do is, the slide says excitation across band gap. So I want to let's say transfer the electron from here to here or from here to here. What do I need to do? What I do is I shine some light. Energy of a photon. So if I shine a photon on this material, okay, if its energy is greater than the band gap, which is the Eg over here, what will happen? The electron which is residing here will go over here. This is known as absorption. On the other hand, if this photon that is coming is falling here, but its energy is less than Eg, what will happen to an electron that is here? Nothing will happen because it requires, remember, it cannot reside in between. It needs at least Eg energy to become free. So what will happen? Nothing will happen. It will transmit. So your material will appear, will not be opaque to this particular frequency. And we know E equal to hc by lambda. So here I'm talking about energies. I can also convert them in terms of, so we put the value of Planck constant and C, and what we can have is a direct relation between the wavelength of the wave, that is incoming wave, and the band gap. So this is a very handy exercise to identify that which kind of wavelength will work for exciting for a given semiconductor. We'll see a couple of examples and this thing will become more clear. How this formula comes, I'll again repeat. E equal to hc by lambda. You just put the values of E and h and C, Planck's constant and speed of light, and you convert them from SI units to EV, and you'll get this expression 1.24 upon E. So any energy can be converted to its corresponding wavelength. And as you can see, E and lambda are inversely related. So we require, for absorption, we require photon energy to be greater than Eg. This means photon wavelength should be less than lambda g, and vice versa for transmission. So this is the complete how does even shining light work. That's how it works. Energy has to be high enough to transfer electron from valence band to conduction band. Okay, so let's solve a numerical based on this very basic understanding of the band gap. Okay, so in this question it says that in an LED, so just hold on a second, excuse me. Yeah, sorry about that. So in an LED, can someone tell me the full form of LED?
Light emitting diode.
Okay, light emitting. Do you know any other type of diode? This will be I think somewhere after 8th or 9th session we'll be talking LEDs in detail. Any other type of diode that any of you might be aware of?
Zener diode.
Sorry?
Zener diode.
Zener diode, very good. Zener diode. These are in fact two of the most prominent, and in fact there's a traditional diode, if you recall, the symbol looks something like this. This is your simplest of diode. This
PN
is
junction diode.
Yes, very good. PN junction diode.
Laser diode.
Laser diode. Is this how it's spelled? Just a second. Photodiode, yes. So in fact, apart from the laser diode, I think all of these will be discussed in this course at different points of time, but they will be discussed. So let's get back to the question, where were we? So in an LED, so as the name suggests, LED is something which emits light, right? It's in the name itself, light emitting diode. So what's happening is that light is being emitted somehow. Okay, we'll see how it happens. In fact, it says that electrons falls from conduction band minima point to a hole in the valence band maxima point. So let me just draw the diagram here. So this is EC, this is the minima, and the question says it falls to here, from here to here. When falling, remember, y-axis is your energy. When falling, this electron must release Eg amount of energy, right? And so I'll write when the electron falls from EC to EV, Eg must be released, and in this case in terms of photon. There can be other ways, but here it is being released in the form of a photon, right? Now we know, and its wavelength is given. So correspondingly, lambda g has been given to us as 365 nanometers. We are required to find the band gap of the material. So it's very simple. We already know that how the wavelength is related to its energy. So we know how much energy must be released, Eg, and lambda g has been given as 365. So I'll simply put these values over here. Remember, this is in nanometers, so in micrometers it will be 0.365 equal to 1.24 over E in EV. This gives me energy equal to, get my calculator, 1.24 divided by 0.365. 0.365. This is coming out to be 3.4 EV. So the E or the Eg in this case, because remember we put lambda g here, so the Eg, the energy, the fall that is 3.4 EV, which is this option. As it happens, 3.4 EV, as I mentioned earlier also, is the gallium nitride material. It's a semiconductor gallium nitride. So in fact the LEDs that you see in your bulbs and in many other places, for instance for decorative purposes, they are made of gallium nitride, right? So this is the gallium nitride has commercialized quite a bit in the past few decades. That's first. Now a similar problem with respect to the again band gap, what the band gap is. So we just understand the band gap is the difference between two bands. We are calling the top band and the bottom band. We saw how it came about when we bring a large number of atoms of any material close together. They tend to split, form two bands, and if they form those two bands, it's a semiconductor. It might also happen, for instance, in case of metals, their conduction valence band overlap. So there is no band gap, right? In insulators, the band gap is very far apart. They're very far away from each other. Okay, so in this problem, we are given three materials, A, B, and C, each with their own specific band gap. Okay, now the question asks which of them should be used to make LED that emits in infrared range. So first we need to, so what's happening is that again same thing is happening. You have EC, you have EV, and when electron falls from here to here, it will emit a photon of energy Eg or of wavelength lambda g. We want this wavelength lambda g to be in infrared range. Okay, so now someone has to tell me what is the infrared frequency or wavelength for that matter. What is visible wavelength? The range of visible wavelength. Come on, you must know this. Anyone?
400 to 700 nanometers.
This is visible. Okay. Visible you say is 400 to 700 nanometers. What is infrared? And what is UV range? This is correct.
Infrared nearly about 600 to 700 nanometers maybe.
Okay. UV?
Okay, sorry sir, sorry.
No, it's fine.
UV must be less than 400.
Yes. In fact, IR is greater than 700. 400 to 700 nanometers are visible, the Vibgeo spectrum that humans can observe. If the wavelength is less than 400 nanometers, it falls in UV, and even in lesser, it falls in X-rays, and I believe there are gamma rays above that. In infrared, I think there is microwaves after this, and I think then there is radio waves. I might be missing one or two, but this is the trend. So here, in this direction, energy increases. Energy or frequency. Remember, E equal to h nu. So if energy is increasing, frequency must also increase. Here, wavelength increases. Why? Because E equal to hc by lambda. So the way I remember is very simple. We know wavelength is 400 to 700 nanometer. And ultraviolet is on the side of violet. Okay, so that's how I remember it should be. And ultraviolet has higher energy than your visible wavelengths. So that's that. So now in this problem we want LED to be in the infrared range. Okay, this means essentially I want lambda G should be, let's say, greater than equal to 700 nanometer. Okay, so I'll put these numbers here. 1.24 upon E should be greater than equal to 700 nanometer. We want in micron, so it will be 700 by 1000. This will give me, this is EG, this will give me EG I cross multiply should be less than 1.24 by 0.7. Let me just make sure I'm correct. Yes, EG should be less than equal to, yeah, so 1.24 So you want such a material whose band gap is less than 1.77 EV. Okay, now we have three materials. So we are given EG of A equal to 3.5 EV, EG of B equal to 5 EV, and band gap of material C is 1.2 EV. We require EG to be less than 1.77 EV. So this means the only material suits our requirement is this, because it's less than 1.77 EV. So this will be our correct option. Okay, now that problem is solved. Now I'll try to do a problem which is not listed here, but let's still do that. Now I want to make a visible LED. Okay, so then this means that lambda G should be more than 400 and less than 700 nanometer, or 0.4 should be less than equal to 1 over EG must be less than 0.7. You solve this, this value will come out to be 1.77 EV, and this value will come out to be 3.1. Sorry, signs have to be inverted. This, so EG band gap has to lie between 3.1 and 1.77 EV for a visible LED. Remember, visible, this means the VIBGYOR, 7 colors of the rainbow. So does it have? So no. So neither of the materials A, B and C will satisfy, because this is 3.5, 5 and 1.2. So none of the materials which are listed in this problem will be able to make visible LEDs out of them. So for this application, these three materials cannot be used. So these are different kind of problems. So for instance, when you appear for your competitive exams, these are the kind of questions that are asked. So not just, so when you're solving this problem, it's fine that you found out that the correct answer is option C. That's not sufficient. If you want to learn, if you want to improve your knowledge, you must ask, okay, what if I want to make a visible LED? Which material should I use? So you see that none of these three materials you can use. Now if you want to improve your knowledge even further, just go ahead and find out which of these materials, just Google this result, which of the materials have band gap between 1.77 and 3.1 EV. That material can be used to fabricate visible LED. Okay, so that's just a tip. I mean, apart from the standard questions that we have. All right, so now, although we solved a few problems, and I told you that you can also refer to in Professor Digvijay's lectures, where he was talking about how a band gap is formed. I told you many atoms come close together and so on. Now let's look at that concept in a bit more detail. Okay, so here is what is called your simple, so just assume it to be silicon lattice. For simplicity, I've just been denoted in a 2D fashion. It will be a 3D structure. Okay, so you can see each silicon atom is covalently bonded to its neighbor. All of them are silicons. There's no doping here. This means all of them are silicon, exact what we wanted, ideal material. Now I want to reduce the problem even further. I want to just consider only one row. Okay, what I want essentially is a 1D system. How will it look like? How will the potential of this system will look like? So you see these are the 4 atoms, which is 1, 2, 3 and 4. And if you recall that the electric potential due to a point charge, remember atom will have neutrons and protons, only positive charge inside it. So I want to see how does it electric field profile look like, just for the sake of drawing it, or other way, to not make it more complicated, there's something called Lennard-Jones potential. It's just for the sake of simplicity, I'll say that the potential will fall as kq over r. That's why you see these hyperbolic curves, and at very last distance the potential will be 0, because any electron which is here will not be able to feel the electric field potential of the nucleus coming from here. Okay, very simply 1 over r. For the sake of simplicity, let's do that. So what you're seeing here is that you see this is for individual atom. You apply principle of superposition. How will the profile look like? It will look something like this. All right, and what are these E1, E2, E3 and so on? These are energy levels. So I'm invoking some quantum mechanics here. Even if you don't know, that's fine. Just assume, just please be aware that there are discrete levels. Energy levels are discrete. That's what quantum mechanics tells us. It's not continuum. For instance, we can say that one energy level in for instance, when we measure the speed, for instance, of a car, we can say speed is 10 meters per second, and some other person can say 10.001 meter per second. There's a continuum there, right? Or energy in joules. The car is having a kinetic energy of 100 joules. Someone will say no, if I increase it slightly, it will become 100.001. There it's a continuum in the macro world. In the quantum world, energy levels are discrete. That's one of the biggest differences between the macro world and the quantum world. The energy levels are discrete. Those are the energy levels you see over here, and these are called valence energy levels. So electrons which are residing here, they will form the so-called valence band, right? And the electrons which are over here, right, they are free to move. They do not feel any potential. They are free to move. They are the free electrons, and they will contribute to what is known as the valence band. Also, you can see what we do is that this is called a Kronig-Penney model. I'll not go much detail into that, but essentially what this talks about is that you can model this kind of electric field profile into rectangular profiles, and then the calculation becomes easier, and what you get is something like this. How to understand this complicated thing? It's very simple. This is for a free electron. H is your Planck's constant. K is your wave vector. This term will come again and again. It is defined as 2 pi by lambda. Lambda is the wavelength. So for a free electron, this is the energy. In the quantum world, this is the energy of a free electron. So when you draw this E versus K, how will it look like? Look like a parabola. So I'm drawing, just follow this red line. This is the parabola I'm talking about. This dashed line is for a free electron. But if you see, the electron is not free, electron is moving in such kind of a potential like this. So what happens is that there are breaks that come about over here. So the blue curves that were there earlier, these are the allowed energies. There is a break in the energies. This is called the band. It's written over here. You see this level, no energies are allowed here. For instance, here also, this is a band gap. This is again a band gap. Electron can be here, electron can be here. It's fine. It cannot be here because it's in the band gap. This energy level is not permitted. Essentially, it's again, as I told you, the fundamental reason for this is that in quantum mechanics, energy levels are discrete, they are not continuous, and thus the bands that when these overlap in the periodic potential, some bands also appear in semiconductor materials. So this is typically known as the EK diagram, and this is another way of representing. I'll not go into this, forget about the right one. This it simply says that it's a parabola and there are some breaks in the parabola due to quantum mechanics. That's it. But if you tell me that okay, now I also have to study quantum mechanics, that's too much for me for this course, fine. Even the people were not very comfortable with this idea that they have to invoke quantum mechanics again and again while understanding as electrical properties of a semiconducting material. So they found a way around. It's a very, how should I say, it's a very ingenious way of trying to solve a problem and just say that okay, we will make some arbitrary entity and we'll say all the quantum mechanics is contained in something called the effective mass. It's also known as m star or m effective. So all the quantum mechanical effects which might give headaches, at least they give to me, effective mass comes to the rescue. They said that all the quantum mechanical effects are just contained in this one number. That's it. And forget about quantum mechanics for this course. That's what happens. So we, in this slide, I'll just tell you, I'll just try to convince you that how does that happen. Okay. This is just Newton's second law. F equal to mass. This is m naught is something called the rest mass and the acceleration. Fine. As we know that any entity, for instance, so what's happening, this is a material in which there are some lattice atoms right throughout, and I'll denote electrons, just a second, and there are some electrons also moving around in this lattice. So these electrons, and let's say I can also apply an external electric field. External, but how? Just hook it to a battery. I called it E external, external electric field. Okay. So what's happening? I'll come back. The total force which is being acted upon by one specific electron is external force which is due to this battery, and some internal force. Where is the internal force coming from? Remember, we just talked about that periodic potential, this thing, right? So it's moving in this material. There are atoms here, so there will be some internal electric field also. But remember, this is the cause of the quantum mechanics and all that stuff. We do not like this. We want to somehow get rid of this. But how do we violate physics? You don't. Simply write the expression of F external, Q times E external, F equal to QE. Similarly for internal, F equal to Q times E internal. There's nothing fancy that I'm writing. And I'll write F external as simply rearrange these terms, F minus F internal. What will it come out to be? What is the value of F? F is m naught times A. And what I now define is that F external, the total external force felt by this electron is this. So I'm removing the effect, all the effect of internal electric fields are being encompassed in this material, in this entity, sorry. I repeat, all the effects, all the force that an electron is feeling due to this internal electric field is being encompassed into just this one entity, M effective. So alternately, I'll draw it like this. Free electron of mass M effective. Again, I'm simply applying a battery, E external. I reduced this problem where the electron was moving under the influence of some electric field, internal electric field, to a problem of electron which is free, but its mass is different. Here the mass is m naught, the typical mass of electron. Here the mass is m effect. Okay, fine, very good. Now I have reduced, I can completely forget about the internal electric field, but that's not how physics works. Now you'll ask, how do I find this number? Good thing is that we do not need to find this number, because this happens to be a constant for a given material. For silicon this is constant, silicon is a semiconductor. For gallium nitride it's a constant, we know that. So physicists figured that out, that effective mass of electron in silicon is this much. Very good, we'll live with that, and we'll not talk about the quantum mechanics or internal electric field anymore. That's the end of story. That's the role of the effective mass. So effective mass essentially is just a way, is just an alternate way of encompassing all the internal atomic interactions, all the potential that an electron is feeling due to the lattice. All that is incorporated into this. So all you need to care about, as I told you, just this. Remember I talked about the free electron E equal to h square k square over 2m. This is free electron. Now essentially just replace m by m effective, and we are good, which is what I'm doing over here. One more thing, I told you people figure out this m effective. How do they figure it out? It's a very simple thing. I'm drawing this conduction Venn as flat. They're actually not flat. All right, okay, so this is a band diagram. I should be very clear, this is a band diagram. This is E, this is X, E versus X. On the right you have is a band structure. These are band structures. E versus K. Where is K? Somewhere, yeah, K. This is the energy E. Okay, so there's a difference between the two. What is this level then? EC. This is EV. All right, and you see this term EG, same here. So this level is EC, this level is EV. What about here? Here this level is EV. This is silicon. On the right you have silicon, this is your EC, and again you see the EG over here. EG is nothing but difference between EC and EV. Okay, these are the EK diagrams. So physicists have drawn the EK diagrams, and we just, how to find the effective mass? Very simple, use this formula. How does this formula come about? Again, same thing. This is for a free electron, right? If you take the double derivative of this, del square E over del K square, this term will vanish, 2 and 2 will cancel, you will get h cut square over m. It's the same as this. Just to illustrate, this is not the proof, this is just the illustration at how this form come into the picture. This term, the double derivative, is also known as curvature. Mathematicians call it curvature. That the sharper the curvature, the more the value. So you see, for instance, this, compare this and this. Okay, we'll solve a couple of problems and then we'll go into this. So right now, but the summary for this part of, we are on to problems now. The summary of this part, effective mass, is that when an electron is moving inside a semiconductor, it feels a periodic potential due to the lattice. There are still atoms inside that, where it's moving the material. In order to, and the energy levels are discretized and so on, their whole quantum mechanical effects come in, which is a nuisance analytically when you're trying to solve problems. So what we do is that we create an entity called the effective mass, just this, which encompasses all the effects of the quantum mechanical effects. The key difference being is that the mass of electron will no more be its free mass, that is m naught, it will be some different mass, m effective. How do you calculate m effective? You calculate it using this expression. So for each material, as on the left you have gallium arsenide, on the right you have silicon. So you see these look different for different materials, and thus we can calculate the effective mass for any semiconductor that are commonly used. Now let's try to put this knowledge to just put this knowledge to test by solving some problems. So first we have the relation between energy and wave vector in the reciprocal space. Just a second. The relation between energy and wave vector in reciprocal space for free electron is, so just a second, for a free electron, remember we are talking about free electron here, right? So I told you free electron energy is h cut square k square over 2m. This is the energy expression. And what's the relation? E versus k? It's a parabola. Okay, this is a parabolic dependence. Hyperbola is 1 over r. And the movement of electron in periodic potential is dependent on, we have already established that. We have already established, again, if you, this is not when it's moving in a periodic potential. Okay, periodic potential means remember that there are atoms in which, and this is moving. This is the model that I talked about, Kronig-Penney model. An electron has to encounter this periodic potential, and to take account of this periodic potential, all of this effect is converted into effective mass. Okay, so if it's a free electron, its mass will be m0. This is free electron. This is electron in periodic potential, where its energy will be discretized, and some of there'll be a conduction band, there'll be a valence band which cannot travel. So for instance, the electrons which are in this level, they cannot travel out, right? They'll be fixed, they'll be tied to the atom, the nucleus, sorry. The rest which are over here are free to move and which contribute to the current, in fact, and their mass is this m effective, which is calculated from this formula. So what we know, for a free electron the relation is parabolic. So this is not correct, this is not correct, and electron periodic potential is dependent on the effective mass, not the real mass. If it's a free electron, then it will have its real mass. Okay, periodic potential, whenever a periodic potential comes, then only effective mass comes, right? Because then only there is a electron is fearing a potential. If the electron is free, it can travel, there's no problem, there's nothing to restrict, no electric fields to influence it. Okay, all right. Second problem in this thread itself is it says that EK diagram of a conduction band of material A is sharper than material B. Okay, so let's see this. Here it's forget about A and B, let's just focus on this. So you see which curve is sharper. Just look at this conduction band curve and the valence band curve. This curve appears sharper, right? So I can say that EC appears sharper, or other ways of saying, that is high. So the sharp curve higher will be this value, del square E by del K square. Okay, and thus lower will be effective mass. I tell you, sharper the curvature, this implies is high. If this is high, effective mass is inverse of that, lower will be the effective mass. And if something has a lower effective mass, so it's very simple, F equal to M effective times A. This F is nothing but your Q into E external. Remember that. Thus the acceleration will come out to be Q times E external divided by effective mass. So if we have a lower effective mass, this means you have more acceleration, or an alternate term, this will come in the further lectures, is higher mobility. Mobility is essentially very closely related to acceleration. So for now, just trust me that this acceleration is nothing but is directly proportional to mobility. So when the effective mass is lower for a given external electric field, if your mass is lower, acceleration is higher. That means you have more mobility. So that's the whole picture. The sharper the curvature, you see the curvature is sharp in this case as compared to, okay. So here we define as effective mass of electrons. Here we talk about holes. What are holes? Holes is nothing but absence of an electron. Remember, I told you at 0 Kelvin all the valence band will be filled, right? But as you increase the temperature, some of the electrons gain sufficient energy that they can traverse this band gap. They cannot again reside here. This is forbidden. But they can go at any given finite temperature. They can go and live here, which will come to in the next slide. But just trust me that this happens for any non-zero temperature. Some electrons travel. They leave behind a hole in the valence band, and they themselves go to the conduction band where they can contribute to the current if you apply any external field. Okay, so here what the moral of the story here was, if we have a sharper curvature, this means material A has the sharper curvature than B. Okay, then effective mass of A will be lower. Okay, so M effective of A will be lower than M effective of B, and thus mobility, this is the symbol of mobility, will be greater than B. Right, so this will be the correct option. Effective mass of A is less than B and its mobility is higher. Okay, this is why we are only talking about electrons. Say it says conduction band. If we talked about valence band, then the story flips. Then we have to talk about holes. The same EK diagram, for instance, you can talk about for this material gallium arsenide here, we are talking about effective mass of electrons as well as holes. In the problem, however, we are only concerned about the conduction band, hence only electrons. You see, everywhere it's written electrons. Electrons in material A, mobility of electrons, electron mobility. Okay, so we are not concerned about holes in this problem. But for the sake of completion, I've also included a diagram in which you can also see holes. So in this you can see electrons have a sharper curvature, right? Sorry, conduction band has a sharper curvature than valence band. This implies the effective mass of electrons will be lower than holes. Okay, in fact, that is the next problem. In n-type silicon, what is this n-type? Forget about that. When we come to doping, we come to it. Let's just say we're talking about silicon and we want to know the mobility of holes and electrons. How do we know that? First, we need to find the EK diagram. So on the y-axis, you have the energy. On the x-axis, you have the wave vector, K. Okay. One thing you notice is that, so in the previous diagram, you see this conduction band minima very nicely aligned with valence band maxima. Such materials where this thing happens are called as direct band gap. Direct means that the maxima of valence band aligns with minima of conduction band. Silicon, you see, the minima of conduction band is here at this wave vector, while the maxima of valence band is here. So they do not have the same wave vector. Such materials are called indirect band gap. Now you will say, okay, so the band gap is 3.4 eV. No, the band gap is the minima of conduction band. So this is a minima, this is a local minima, this is a minima, global minima. So global, you have to take the minima, you have to take the global minima of the conduction band, not the local minima. Similarly here, the valence band here is shown only one maxima, it's here. So this will be the Eg. I'll repeat, Eg is the difference between the energies of minima, global minima of conduction band and global maxima of valence band. So it will be 1.12 eV, not 3.4. So please keep that in mind. And when such a thing happens, when the wave vectors are not the same for global minima and global maxima, those materials are known as indirect band gap materials. Germanium and silicon are indirect band gap, and they do not make very good LEDs. Gallium nitride is a direct band gap material. It makes very good LEDs. So that's a question, that might be a question. In fact, that's a very famous, I mean not famous, but that's a prominent question among your competitive exams. Which of the materials can be used to form LEDs? Which of the materials are direct band gap? So on. Okay, so what we see is that, so now when we talk about mobility, so remember what we talk about. So let's compare curvature. Conduction band is sharper than valence band. This is the conduction band we have to look at, not these. Look at this and look at this. This is definitely sharper conduction band, right? So conduction band is sharper than valence band. This implies M effective mass of electrons will be less than M effective of holes. Right? Remember, because curvature is nothing but del square E over del K square, and M effective is inversely proportional to this. Remember that. So effective mass of electrons will be less than effective mass of holes. And we talk about mobility. Mobility is inverse of effective mass. So mobility of electrons will be greater than mobility of holes. That's how we solve this problem. This is the logical flow. Sometimes the question may ask in reverse, that the mobility of holes is this much, which have the higher effective mass. That's why I'm writing in this manner, so that you are able to comprehend, you are able to solve problems which are similar. Okay, and one more thing in this problem, although the problem is complete, the mobility of holes is smaller than, so the correct answer would be this, smaller than. Another thing that you notice here is something very peculiar written here. So I'm writing now in blue, is the heavy holes and the light holes. So there are two kind of holes that we're talking about in this silicon at least. How does this come? Heavy and light comes from mass. What is the mass? Where is the mass coming from? Again, 1 second. Okay, so again you see the curvature of this, let's say curve 1 versus curve 2. Curvature of this second curve is higher, sharper. So if again the same logic, the effective mass for this curve, for curve 2, will be lower. Again I'll write this, curve 2 sharper than curve 1. This implies M effective of curve 2 should be less than M effective of curve 1. So that's why curve 1 has heavy holes, curve 2 has light holes. So such type of problems can come, that you have to identify which hole is heavier, right? Just so now you can hopefully this. Okay, so till now we have talked about what is a semiconductor, the origin of band gap in a semiconductor, the band structure of a semiconductor, and the effective mass. So I'll take a pause here. If you have any doubts or comments, you may ask, because the next topic I'm going to start is the Fermi function. That's just more of a statistical construct. So the physics, there is less amount of physics involved in that, but here it was more physics heavy. So that's why I'll be pausing and I'll wait for your comments or questions. Feel free to ask. All right, let's go ahead then. The final topic for today is Fermi function. What is a Fermi function? It's a probability distribution function. Okay, what is that? Fine, I'll write it and then you can understand. Essentially, it's saying that for a given energy, what is its probability? Probability of what? Probability of finding an electron at any given energy level E. Okay, let's try to follow this blue curve. Forget about the expression for now. Let's try to follow this blue curve. Okay, so what we see at, let's say at some this energy level, let's say I call this E1. At energy level E1, what is the probability of finding electron at energy level E1? How do you find that? Simply you just extend it and you'll find it somewhere over here. This value is very close to 1, so I'll write it approximately 1. Okay, again I'm just following the blue curve. Remind T equal to 300 Kelvin. Let's find the probability of finding electron at EF just by looking at this curve. At EF is here, so I'll extend this. This is this 0.5 equal to 0.5. Let's say some other level E2. F at E2, this will be equal to somewhere over here. Let's say this value is 0.2. Okay, this value is let's say 0.1. This is what it's doing. I'm just plotting it here. How does this numerical values come into the picture? They come through this formula. And remember, these three values that I have written are for T equal to 300 Kelvin because I was following this blue curve. Right, something interesting happens at T equal to 0 Kelvins. That's where in fact an alternate definition of Fermi function comes. So let's put T, let's do that in fact. What should be the temperature in Kelvin for all the energy states above the energy level, Fermi energy level, to be empty? This is also known as a Fermi Dirac system, by the way. The expression that you saw, the mathematical expression over here, this is also known as Fermi Dirac distribution. Electron is a Fermi particle. Okay, so it follows a Fermi Dirac distribution. There's something which has particles which are called bosons. Those follow, I think, Bose-Einstein. So people from physics background may be able to relate a bit more, but that's how it works. Okay, so now let's try to do this. So now it's a Fermi Dirac system. This means we'll use that expression in the exponential expression in the previous slide. Now we need to find a temperature for all the energy states of the Fermi level to be empty. Okay, so we need to find the temperature. So the problem is find T such that Fe greater than EF equal to 0. Whatever is written in words here, what should be the temperature? Find T such that energy states above Fermi energy level, this means probability of finding an electron in any energy E greater than EF should be equal to 0. So if I use this formula such that Fe greater than EF should be equal to 0. So let's do that. So I'll put this 1 plus exponential E minus EF over KT. Remember, E is greater than EF, so E minus EF must be a positive quantity. Okay?
Sir,
Yeah?
what is meant by Fermi Dirac system?
Okay. So as I was mentioning that in the physics there are some fundamental particles. I'm not able to recall. If someone of physics background may help me, but there are some fundamental particles. For instance, what's that called? There are some every particle like electron, proton, neutron, and so on. They are made up of something called quarks. Okay, in that universe, in that classification, there's a classification called fermions. Okay, from there it has been found that fermions follow Fermi Dirac kind of distribution. So okay, so distribution part you understand. Distribution means you see electron we cannot predict due to Heisenberg uncertainty principle. We cannot simultaneously predict the position and the momentum. So there is something called delta x times delta p should be greater than equal to h cross over 2. Okay, so it just so happens that for fermions, you know that two electrons, the Pauli's exclusion principle is one of the I mean it's closely linked to this. So fermions are such that they cannot, the two fermions, if they are occupying the same space, one has to be spin up, other has to be spin down. There's much more formal definitions of these systems, but essentially the fermions follow a distribution called the Fermi Dirac distribution. Now what is a distribution? We talk about an electron here as if only one electron exists. No, that is not true. In any material, let's say we talk about silicon semiconductors, there are around 10 to the power 22 atoms in 1 centimeter cube. How much is 1 centimeter cube? 1 centimeter cube is your thumbnail is 1 centimeter cross 1 centimeter. So in that small box, there are around 10 to the power 22 or Avogadro number of atoms. Okay, and a similar number depending on the temperature, 10 to the power 16 or 10 to the power 18 number of electrons. Okay, especially if you dope them. In such high number of electrons, we cannot specifically say that this electron is here. No, we say that okay, 20% of the electrons are here in this energy level, 30% of this energy level. That's what we call a distribution, and that distribution depends on temperature. So this what you are seeing here is a Fermi Dirac distribution, which is expressed using this mathematical expression. All right, so essentially what's happening is that there will be, let's say, 10 to the power 10 electrons. When we say the probability at, let's say, at some given energy level E1 is 0.2, what this means is that essentially they are 0.2 10 to the power 10. This implies 2 into 10 to the power 9 electrons are likely to be found. Not exactly found, likely to be found. That's what a distribution means. But because when we are talking about when we are trying to understand a system, it's better to do in probabilistic terms, not in absolute terms. This is absolute terms, 2 into 10 to the power 9. When I talk about probability, I'm focusing only on one electron. There is a distribution, but here I'm focusing on one electron. More details, unfortunately I'm not able to recall of the Fermi Dirac system. I'm just able to recall that there are something called fermions, which follow that they cannot have the same what's that called, quantum numbers. So if one is spin up, other is spin down. However, this is fermion. For boson, there can be more than one. In same energy state, this is some energy level E1. This is again, let's say, some energy level E1. An arbitrary large number of bosons can sit in one energy level. So that is a key difference that I'm able to recall. Fermi Dirac, I'm not able to recall apart from that. I'm sorry, I cannot help you. That's what I'm saying. If there is anyone from physics background, I'd request you to speak up so that this gets cleared here itself. Otherwise, I'll just read a bit more about Fermi Dirac and the next session. Just please remind me in case I forget. Drop me an email or just ask in the start of the class itself. Okay? Is that fine?
Okay, sir.
Yeah. Okay. So we are given E greater than EF. This means this is a positive number. Okay. So let's say this positive number, let's say to be N. Anything. It's a real number, it will be positive. So this means K is a positive, it's a Boltzmann constant. Temperature is positive because you're putting temperature in Kelvin. So please understand this is a positive quantity. Okay, and I just I'll write it like this. Has to go to infinity. For this to be equal to 0, this entity has to go to infinity. When will this go to infinity? See, n is a positive number. Small, large doesn't matter. K is a constant. T is the thing only in our control. When will this unconditionally go to infinity? That means it does not depend. When t goes to 0. When t goes to 0, then you are 100% sure whatever be this value of n, right, this exponent will always go to infinity. E to the power infinity is infinity. So when temperature will go to 0, this exponent will go to infinity, right? This exponent will go to infinity, and thus Fe, the probability, this probability will come out to be 0. The temperature, this is the temperature we are talking about. Alternately, this is a definition of this Fermi distribution function from where it comes. At 0 Kelvin, the probability of finding electron in energy greater than EF is 0. Now you see this solid black line. This is corresponding to T equal to 0 Kelvin. For all energies above EF, the probability is exactly 0. Right? And for all energies below EF, the probability is exactly 1. That's why this Fermi level is also defined as, Fermi level is the energy level where up to which the electrons are completely filled at 0 Kelvin. I'll write that. This is the alternate definition. Fermi level is the energy level up to which remember at 0 Kelvin. This is very important. At 0 Kelvin, because if you raise the temperature, you see there are some electrons which you can find. For instance, in this blue curve, there will be some electrons, some finite probability, right, of finding an electrons with non-zero probability. So that is what is. So that's why T equal to 0 Kelvin. It's a hypothetical thing, Fermi level. So we'll see in the next session. When we talk about Fermi levels, it actually sometimes falls in the energy band, forbidden energy gap. So you'll say, it doesn't even make sense. You cannot, first you say that there cannot be any energy states in the forbidden gap. Now you say it can be filled up to that. We'll encounter this contradiction, seemingly what seems contradiction. We'll encounter in the next session, hopefully. But this is basically an alternate definition for Fermi level. Repeat, Fermi level is energy level up to which all electrons are filled at 0 Kelvin. All electronic states are filled rather at 0 Kelvin. Okay. Similar problem now. The probability of finding an electron below the Fermi level, at Fermi level, and above Fermi level at 0 Kelvin is. So in fact, we solve this problem here. At T equal to 0 Kelvin, this is the curve we are talking about. Above the Fermi level, T equal to 0 Kelvin, probability should be 0. Above the Fermi level, Fe greater than EF should be 0. And you can try that. You put E greater than EF, that's what we solved, right? And I'll solve this formally again. So this is 1 plus exponent of, again, some positive quantity n over k times 0. We're talking about 0 Kelvin. 1 plus exponent of plus infinity. This is plus infinity. This will come out to be 0, right? Now I'll use the second color for below Fermi level. E less than EF. Let's see what happens. 1 plus exponent of E minus EF over k times 0. This will be 1 plus exponent of, remember E is less than EF in this case now. This will be some negative quantity. Let's say some minus m over k times 0. So this will turn out to be 1 plus exponent of minus infinity. This m is a positive quantity, k is a positive quantity, this is 0. This will be minus infinity. E to the power minus infinity is 0. So the probability of finding an electron below Fermi level at 0 Kelvin is 1. Alright, now let's do the third problem, which is E equal to EF. 1 plus exponent of E minus EF over K times 0. This is a 0 by 0 form. You solve it using that's a 10th or 12th class mathematics. I'm forgetting that. You try to solve this. This will turn out to be 1 plus 1 by 2. Again, this is one more definition of Fermi level. Fermi level is the energy level at which the probability of finding the electron is half at any temperature. That's a key difference. Fermi level is the energy level at which the finding the probability of electron is half for any temperature. So you see this, you see T equal to 300 Kelvin, it's half at E equal to EF. For T equal to 0 Kelvin, it's also half. You draw any line, it will always pass through this point. Why this happens? Because when you put E equal to EF, the numerator will become 0. As simple as that. Okay, so what we found out is that below Fermi level is 1, at Fermi level is half, and above Fermi level is 0. This is for 0 Kelvin, mind you. This problem here we're solving for 0 Kelvin. But again, we saw one more definition of the Fermi level. There's a lot of confusion at what is the Fermi level. Different people define it a different way. I am also a confused person. I remove my confusion by just removing this diagram on the right hand side. That's it. If you keep this diagram in your head, that's it. You will never be confused, because this contains all the picture, all the information that you need to know about Fermi level for different temperatures, above energy level, above Fermi level, below Fermi level, at Fermi level. All the information that you require about a Fermi level is contained just in this plot, E versus Fe. Simple. Okay, right. How much time? Okay, we have still 17 minutes. I think I will be able to finish in time. Okay, any doubts regarding the Fermi level? I mean, the till now I have been putting T equal to 0 Kelvin. Okay, but there are different problems that we encounter, and the next 3 problems are in fact related to that. But before I go into that, if you want me to repeat a problem, repeat some concept, any random temperature you want me to solve it for, it's all fine. It's okay, because the problems that I'm solving these are some standard problems. In fact, even the assignments, you might find problems related to this. Solving assignments is one thing, understanding a concept is another thing, especially if you are appearing in competitive exams, because there some questions do repeat. I'll agree to that. In fact, I benefited because some of my questions, when I was writing the competitive exams, some of the questions were repeated. So I was very lucky in that sense. Many times the questions are not repeated. In fact, most of the questions are new, but the concepts cannot be generated out of thin air. Concepts have to still remain the same. So if you understand what is a Fermi level, that's what I told. Just based on this diagram on your right, everything about the Fermi level is contained in this, just in this plot. So if you understand this, any problem related to Fermi level comes in your exams, either assignments, your university exams, your competitive exams, your job interviews, anything, you'll be able to tackle it, right? And once you try to see Fermi level from different perspectives, right, then you create a comprehensive picture. I understand that at the very first time you might not be able to do that. It is confusing. It was confusing. Sometimes I still get confused, but when I see this diagram, my doubts just disappear. That's all. Then so that's what my advice is. Okay, right. So now we have the another problem related to the Fermi Dirac statistics, as it's called, the probability of finding an electron for a given energy level, right? So the probability that an energy level is occupied by an electron if the state is, just a second, if a state is above the Fermi level by 10 kT. So what I have to do, I only know one formula, but E in this problem is given as EF plus 10 kT. That's given in the problem. If the state is above the Fermi level by 10 kT, so I have to find given E equal to EF plus 10 kT, what is FE? And remember, FE is probability at E. It's also known as same thing, probability these two terms are used interchangeably. This is what I have been speaking, probability of finding an electron at E, right? Alternately, it's like the probability that energy level E is occupied by an electron. It's like saying a person A is sitting in chair, passive voice, chair is occupied by person A, same thing. Active voice, passive voice, but there are two ways in which this is presented, hence I'm writing this here for better clarity. Okay, now this is just putting the numbers. So we need to find f of E, this means this expression, and now 1 over 1 plus exponent of E minus EF. So the value of E is EF plus 10 kT minus EF over kT. This will be 1 plus EF will get cancelled out, 10 kT over kT, 1 plus exponent of 10. So exponent of 10 will be a large number, I believe, maybe a few thousands. Let's check. Exponent of 10 is 22,000 around. Okay, so this means this number will definitely be less than half, which makes sense. Why it makes sense? Remember this diagram. This is E versus FE. This is half. For all energy levels above EF, the probability will be less than half. Simple as that. What is the energy level here? Energy is EF plus 10 kT. So we are above EF. So the probability will naturally be less than half. That's why I said. Okay, so numerically what this is this is coming out to be 4.5 into 10 to the power minus 5. This. Actually, what I should have done is I should have eliminated these options altogether. Okay, one more thing. When you have multiple choice questions like this, especially in competitive exams, to save time, if let's say the options were 0.5, 1, 0.75, and let's say 10 to the power minus 5, I would not have solved this problem. I would have directly taken this. Why? Because I know The energy level we are talking about is above EF, and above EF the probability must be less than half. I would never have solved this problem. I would have blindly taken 10 to the power minus 5. Okay, also if none of the above would have been there, then I would not have done that. Why? Because what is the coefficient here? Here the answer is 4.5 e minus 5. But if this option were not there, 10 to the minus 5, 0.5, 1.75, I would have blindly taken 10 to the minus 5, saved my 2 or 3 or 5 minutes, which I could have given to the topics in which I am not comfortable in. Keep these strategies in mind. This is not a shortcut. Trust me, this is not a shortcut. This is based on an understanding. You remember this graph, and based on the understanding, you are saying, okay, these three options cannot be true. The only option remains is this. All right. Right. So yeah, this is a fairly straightforward problem. We were given to find the probability of an electron in some energy state E, which is 10 kT above EF. We put in this formula and we note that the value is 4.5 into 10 to the power minus 5. This is the probability of finding an electron. Just as I told you, a thought exercise. Let's say there are total 10 to the power 18 electrons in lattice. How many of them will be in this state, this energy state? They will be 4.5 into 10 to the power minus 5 into 10 to the power 18. 4.5 into 10 to the power 13 electrons will still be there in this state. That's what I was saying. It's a distribution. Please remember that. This is a huge number of electrons which can contribute to current, provided that's what the purpose of this level is. Okay, still there are a huge number of electrons that can be put to use. So just probability itself in this context is just a number which you cannot relate physically. But please always remember, this is a probability of finding an electron. The number of electrons usually in a lattice are huge, 10 to the power 14, 16, 18, 20 in extreme circumstances, 10 to the power 20. There, even if you multiply a small probability of, let's say, 10 to the power minus 5 or 10 to the power minus 6, you still end up with a huge number of electrons, which you can utilize to your purpose, to your application. Okay, that's what I mean to say. Probability, finding the probability is one thing. Absolute numbers is a completely different story, and we'll see that when we try to solve problems of diode and MOSFET and so on. This thing will come into the picture over and over again. We'll not have a probability there, but we'll talk about the absolute number of electrons, and then you'll be able to appreciate that even though the probability is 10 to the power minus 5, 10 to the power minus 6, the number of electrons are still huge, which are contributing to the current. Okay, we have 5 minutes, should be fine. Okay, so the problem says that assume the Fermi energy level is 0.5 eV below conduction band energy. So let me draw the band diagram first. This is EC, this is EV, and this is your EG, the forbidden energy gap. EF is somewhere over here. Usually we denote EF by this dotted line, and it says Fermi level is 0.5 eV below conduction band. So this is 0.5 eV. Determine the probability of state being occupied by an electron at EC. So we have to find the probability of electron having an energy EC. Very simple. How? Use this formula. So I put E equal to EC over here. 1 plus exponent of the value of E is EC minus EF over KT. 1 plus exponent of, what is EC minus EF? EC minus EF is this. It's given in the problem itself. 0.5 EV. What's the value of KT? KT is also given. So this is a good thing to remember. At T equal to 300 Kelvin, KT is 26 milli electron volts. If you see Professor Digvijay's slides, lectures, he keeps on referring to this number. It's a good practice that KT at room temperature is 26 MeV. So I put this here 0.026 EV, and now I just need to solve. Give me a minute. So this will be 0.5 divided by 0.026, exponent of that. Okay, we can ignore +1, and if I take the inverse, it's 4.45 into 10 to the power minus 9. So this option. Again, remember, we are talking an electron being found here, which is above EF. So the probability has to be less than half. So these two options are eliminated again. Remember this. EF, probability here is half. This is E versus FE. And we are talking about energy which is above EF. So we are talking about somewhere over here. So probability will naturally be less than half. Two options were there, calculated 4.5, 4.45, 10 to the power minus 9. Straightforward problem. Right, so last problem for today, I think. Yeah. Okay. So what we have here is at 300 Kelvin, determine the probability of energy level 3 kT. Determine the probability that level below 3 kT below Fermi level is unoccupied. This time I'll start with this. This is E versus FE. EF half. Okay, energy level 3 kT below Fermi level. So we are talking about an energy level which I'll draw in blue color here. This clearly I know that FE, let's say this, call this energy as E naught. FE naught is greater than half. We are required to find the energy that it's unoccupied. Okay, I told you the probability of finding an electron, probability of occupation is the same thing. We need to find that it's unoccupied. So what we need to find is 1 minus FE naught, probability that E naught is unoccupied is this. What's the value of FE naught? FE naught I can get from this. So this will give me FE naught equal to E naught minus EF over KT. What's it? It's 3 KT below. So this will be minus 3 KT over KT. This gets cancelled. So this will turn out to be exponent of minus 3. You add 1 in that. 1 divided by answer. This is coming out to be
0.952.
yes, 0.9526, let's say. But we need to find 1 minus FE naught. So 1 minus FE naught is coming out to be 1 minus 0.9526. This will be close to 0.05. 0.05. This cannot be there. Yeah, 4.7. If you solve this, actually it will come out to be, I think, similar to that. Yeah, if you solve this, it's coming out to be 4.7 E minus 2. 0.047, let's say. So it's that. Again, this time I first made an educated guess where it's going to lie. It cannot be this, because I went ahead and solved this problem. Okay, so just again, I told you that this diagram is very handy, and that in each of the problem, if you recall this diagram, you can solve. And sometimes you can eliminate options and save yourself some trouble, especially in competitive exams or where there is a time crunch. All right, so that is all from me. We are on time. Thank you for staying back. I'll repeat that I'll upload this session on my YouTube channel. I'll again share the link for that as well as my email ID. Just hold on a second.
Sir?
Yeah, go ahead. Just 1 second. Let me just share that
Yes, sir.
email ID and the YouTube channel. So yes, BB Rao, I'll be uploading these recorded sessions. I cannot say because there's a small editing that I have to do, but I'll upload it today's Saturday. I'll try to upload it within the 2 days of the session. So hopefully by Monday I'll try to do that. Okay, for each session, that is. And the second thing, I have my email ID here. If you have already have a discussion forum, I believe, for the course. If you still need some specific doubts that you don't want to ask in the discussion forum, and as I told you, some of you, I asked in the start of the class, some of you had said that not just for the doubt clearing but also for some guidance, for instance, let's say competitive exams and career perspective and so on. So in case you want to chat about that, just feel free to email me. That's all from me. Yeah, somebody was, I forgot, sorry who that was. Please speak up again. Okay, it's fine. That's all
Sir.
from, yeah, Rajesh, go ahead.
Sir, is that Fe versus P graph taken at 300 Kelvin temperature, which is constant?
Sorry, can you please repeat?
That reference graph, energy level versus probability to find electron, that graph, sir.
Yes.
Is that taken at constant temperature or?
No. So okay, let me open the slide again. Just hold on a second. So okay, this one. So this is, for instance, in this plot you see only two temperatures, T equal to 0 Kelvin, T equal to 300 Kelvin, right? So let's say I want to use one more temperature. One second. I want to use one more temperature. Let's say the temperature is 100 Kelvin. So how will its plot look like? Its plot will look something like this. It has to cross half here, like this, and then it will go something like this. So green is 100 Kelvin. So for each temperature you can draw here. In this plot earlier I had shown only T equal to 0 Kelvin and T equal to 300 Kelvin. So that, to keep it simple, 0 Kelvin is the absolute because many definitions are according to the 0 Kelvin curves. T equal to 300 Kelvin because the most not the most, a large number of experiments are conducted T equal to 300 Kelvin room temperature. So that's why I just report those values. But for you can draw in this plot for every temperature. That doesn't matter. The story will remain the same. Below EF, for energy levels below EF, the probability will be more than half. Probability of occupation will be more than half. For Fermi levels above EF, the probability of occupation will be less than half for every temperature. Simple. You can draw that.
Thank you.
Yeah. That was a good question actually. Thank you for asking.